Hey there! We're in Unit 7, Lesson 15 today, and we're going to be talking about something called z-scores. Now, z-scores are going to take an idea that we've already talked about with standard deviation and mean. We've talked about that many times this unit. And we're going to see that a z-score is really just telling us how far a value is away from the mean in terms of how many standard deviations it is. So far we've already been talking a lot about this normal distribution curve and how we can draw it many, many times and find lots of percentages and probabilities based on how far away a value is according to the number of standard deviations. So we've got the mean right here in the middle. I want to remind you that this little character, this Greek character called mu, is the mean. We always put that right in the middle. And then we can divide these chunks into 3 even parts like this using that standard deviation. So that tells us how spread apart our data is. And so far we've been able to calculate some values knowing that things like with our empirical rule that 34% of data is going to fall within 1 standard deviation below the mean type thing. What we're going to see with the z-scores is that we don't have to be locked into these standard deviation values. We can find a value, say, right here, that is between 2 standard deviations, and we can give it this thing called a z-score. What it's going to tell us is how far away this value is from the mean according to how many standard deviation chunks we need to use. So if we think of 1 chunk of standard deviation here, it would be a z-score of a positive 1. It's positive because it's to the right of the mean, and it's 1 because it's 1 full standard deviation. But this data point right here is another half, right? See how I need another little half of a standard deviation to get to that data point? So this data point here would actually have a z-score of positive 1.5. Similarly, if we were going to something over here on the low end, I'm going to say that I have a data point right about here. And I can see that it has to go, first of all, negative. So I'm going to have a z-score that's a negative value, telling me that it's below the mean. And I have to go 1 full standard deviation chunk, a second full standard deviation chunk, and then about another third. Okay, so this one might have a z-score of negative 2.3-ish. Now, a lot of you have heard me use the ishes before, and we're going to see that we can find something that's a little more specific than that. So keep this idea in mind that a z-score is just how many standard deviation chunks we are away from the mean. And so we're going to look at a situation starting here in Lesson 15. And what I see is that we can use, it's telling us we can use a table, but we're going to get even better than a table. We're going to use one of the tools that Illustrative Math has provided for us to actually get some good calculations going on here. So, a factory is producing baseballs. The weights of baseballs produced are approximately normally distributed with a mean weight of 145. Good information to have. There's our mean of 145. And a standard deviation of 2 grams. So there's our mean of 145, ooh, terribly written, with our standard deviation of 2 grams. This is the information that we're going to need so far. Okay? Official rules require baseballs to weigh between 142 and 149 grams. We're going to try to remember that idea for a little bit later in our question. Okay? So, first of all, what we're going to need to do is convert something to a z-score. Now, I've already given you an introduction, but let's put some real numbers behind this, okay? So, I'm going to get rid of that one. And so a z-score is used with this equation. This is a great equation to write down. You're going to need it for all of your practices, okay? So we take whatever value we're looking for. We subtract the mean, we find the difference of it between the mean, and then we divide it by whatever the standard deviation is. That again will tell us how many of those standard deviation chunks we need in order to get to the data point we're looking for. So, in our value, in our example here, our mean is 145, and our standard deviation was 2. So, to find the z-score of 142 grams, I'm simply going to plug it into this equation and solve it on out. So I've got 142 minus 145. That value is going to give me a negative 3. Okay. And then I'm dividing it by my standard deviation of 2. So negative 3 divided by 2. That's going to tell me that it has a z-score of negative 1.5. So I need a full standard deviation and a half to get there. So negative 1.5 for 42 grams. That's our z-score. Our z-score for our second one, here's another example for you right back to back. To find one for 49 grams. Again, we're just going to plug it into this equation right here. So I've got 149 minus the mean. I'm going to go ahead and just do this in my head. 149 minus 145 gives me a value of 4. Dividing it by the standard deviation of 2 tells me that 149 has a z-score of 2. It is 2 full standard deviations above the mean. Okay, so this one's negative, it's below the mean. Our second one is positive, it's above the mean. We can also give something a z-score and figure out what data point goes along with it using the same idea here. This time I don't know what the value is, but I know I'm going to subtract the mean of 145, divide it by my standard deviation of 2, and I want this z-score to equal 1.45. So that's what this question is asking me. It's saying, hey, what is 1.45 standard deviations above the mean? My answer better be above 145 because it's a positive z-score. Keep that in mind. So my first step to unwind this problem, to start solving it on out, I see that I am dividing by 2 as my last step over here, so I need to multiply everything by 2. So I have an unknown value, minus 145. That is going to equal 2.9. Okay, so I have an unknown value minus 145 equals 2.9. Just doubled both sides, right? Multiplied by 2 to get to cancel out over here. Then I have to multiply this guy by 2 to get that 2.9. Okay. So my next thing to do is to take my next step. I see I'm adding, so to unwind or I'm subtracting, so to unwind subtraction, I need to add 145 to both sides. So the value that I'm looking for that's going to have a z-score of positive 1.45 is going to be 147.9. Almost 148, which makes sense because 1.5 z-score should be at 148 exactly. This is 1.45. All right, so, but let's keep that in mind. We're going to keep using these numbers of 142 and 149, because remember that's the range that we're given that baseballs can weigh to be used in an official game. Okay, so 142 had a z-score of negative 1.5, 149 had a z-score of 2. Let's look at our next idea. Okay, so it tells us about this table giving area under a normal curve. Right, so they've created this normal distribution curve for us with our mean right in the middle at 145 and our values at 142 right here. Okay, what a z-score can use, if we used one of these tables, it would tell us the area under the curve over here. That tells us, again, probability. Okay, but this was a z-score that was negative 1.5 was our z-score here. All right, so we have this cutoff at 142. The next question that's going to ask us, I'm going to pop it up here, it talks also about shading the region that's given for a table related to 149 grams, right? Ultimately, what we're going to be looking for in this question is what is our percent of baseballs that this factory is making that is between the normal range that we can use, right? The range that is from 142 to 149. Okay, and this was a positive 2 z-score. All right, so 142 is actually closer to the mean than 149 is. I know because it has a lower z-score, but something to keep in mind. But really what we're looking for is what is the percent that of the baseballs that they make in here that fall between these two values. Ultimately, that's what we're trying to solve. How many of their baseballs can actually be used? All right. So if we found using a z-score and a table, the area under that curve, we could make that calculation. All right. Let me show you what illustrative math gives us to help us do this. So it gives us under this, right under my head here, this Math Tools button, this purple Math Tools button. One of the math tools that it gives us is the probability calculator. Okay, so if you are at im.kendallhunt.com and you go to the high school curriculum, you'll find under Math Tools this probability calculator. It takes you to this idea right here. Okay, and this probability calculator has some questions for us. You should see it very familiar. Normal curve set up, mean right in the middle, standard deviations off to each side. It lets us put in what we know, the mean and the standard deviation. So in this case, we know that the mean is 145, and we know that the standard deviation was 2. So I just put in some of those values here, 145 and 2. And I'm trying to find the probability, how many of the baseballs they make in this factory that are between 142 and 149 grams. So notice I'm putting those two numbers in here, 142 to 149 grams. And what it does is, you see how it shaded that area under the curve for me? Really helpful. Because what that tells me now is what is the probability that the baseballs chosen at random are going to fit within that range from 142 to 149. Okay, and it tells me that it's 0.91. So what we're looking at is that 91% of their baseballs are going to fall within that range. Okay, so this is a really nice tool to use that's going to help me out. Now this doesn't show us the z-scores of what's happening in between there. Okay, but I could also go back to this idea that our mean is 0 and our standard deviation is 1. If my low end that I was looking at, remember 142 had a z-score of negative 1.5, and my value at 149 grams had a z-score of a positive 2. Okay, now that was from way back in one of our first screens right here. 142 had a z-score of negative 1.5, 149 had a z-score of positive 2. So putting those z-scores in also tells me that same percentage. Now that's a really key idea. So you could use your z-scores here with a normal distribution with a mean of 0 and a standard deviation of 1. Tells us how many standard deviations we're looking at. So the end of this lesson asks us some things like finding those areas and finding the difference, right? And so the proportion of baseballs that the factory makes that are within official rules would be that 91% that we're finding, or 0.91. Right, just putting an or in there. So that kind of gives us a great sense of what we're looking at. Z-scores ultimately allow us to compare apples and oranges. Okay, so we've been talking a lot about data and statistics, but sometimes we can't always compare the exact same things. So far we've been looking at baseballs and baseballs, but in some of your practice coming up, you're going to be comparing z-scores like here on Khan Academy. And so they're comparing ages of people in the Senate and people in the House of Representatives. Now this is true data, so some pretty interesting things, right? People who are members of the Senate tend to be later in their careers than they are in the House of Representatives. So here's their summary. The Senate has mean of 62 years old with a standard deviation of 10. House of Representatives, 58 years old with a standard deviation of 11. And we want to figure out, like, hey, if we pull this Senate minority leader, he's 66 years old. I should say they, because I don't know if it's a he or a she. The Senate minority leader, they are 66 years old. And the House of Representatives minority leader is 76 years old. We want to know relative to their group, each unique group, which leader was older. So let's think first about this Senate minority leader. This person is 66 years old. According to the Senate age, that means they are 4 years higher than the mean. Okay? 4 years higher than the mean in the Senate. And if I were to divide that by the standard deviation of 10, this tells me that I have a z-score of positive 0.4. Okay, so this person is older than their average for their group. When I look at the House of Representatives, this person is 76 years old. Now comparing that to the mean, 76 years old minus 58 tells me that this person is 18 years older than the mean. So I'm going to put that positive 18. They're above the mean, they're 18 years older. And their standard deviation is 11. So this one has a little bit more spread out, a little bit more wiggle room. And when I do 18 divided by 11, I get a z-score of a positive 1.64-ish. Okay. So found the difference from their age to each of their respective means, and then divided by their respective standard deviation. So, relative to their group, which leader was older? Well, this person in the Senate was only, they're less than half of a standard deviation above the mean. This person is way more than one standard deviation above that mean. So they are much farther outside of what we would expect, so they had to go more standard deviations. So, which leader was older relative to their group? Definitely this guy. He's got a higher he's got a higher z-score. So my House of Reps minority leader is the one that is older relative to the rest of the people in his group. Got it, right? So z-scores can help us compare things that aren't exactly similar, or they're from two different data sets. So you'll see some other ideas here where it's going to ask you to practice calculating z-scores. Remember our formula that you're going to need to have on hand as we do that. Value minus the mean divided by standard deviation. And then it's going to ask you to put it into use about comparing different elements to their groups respectively. All right, let us know if you have any questions. We're here to help. Thanks.